And we'll just start by solving the remaining integral problems we didn't get to last time. And that means we'll start with exercise 11, where we have an integral that is called the integral of x to the third power
times the square root
a quarter of x to the fourth haven't we done 10 either? Okay, I'll do the 10th after the 11th. So we'll see why we should go out. So the integral you see here, the idea is to notice that there's a pattern. And the pattern is that if you took the inside, what's here, and differentiated it, you'd get x to the third power. Because a quarter is x to the fourth, if you differentiate it, the quarter stays. 4 gets multiplied in front, and 4 times 1 quarter gives 1, times x raised to 1 less than 4, which is 3. And the constant term, differentiated, gives 0. So all that you see here, we can call it t if we like, and that's what we call introducing a new variable. We simply replace this with a new variable, hence the method is called substitution integration. So we can create a thought bubble here where we say, I'll set t equal to 1 quarter x to the fourth and plus 2. And what you do inside the thought bubble is you differentiate t with respect to x to see what you get first. And we write it like this. d times x, it means I'm differentiating t with respect to x, and t is this. Then so if I differentiate t, then I differentiate this part. Here you'll see that it gives x to the third power because it's a quarter. Multiplied by 4 gives 1, and then 1 less in the exponent, so it gives x to the third power. Then I multiply dx to the other side of the equation and isolate the size dt. So I consider this here as a fraction. So I get that dt equals x to the third power times dx, and then my thought process is over. Because now I can see that x to the 3 times is exactly what's written here. Inside that slightly weird bubble, there's x to the 3 times dx, and that's also what's written here. So apparently that can be replaced with dt, all of that, because I chose to call that t. So I get a new and easier integral called the integral of the square root of t, because this was t, and the rest became dt, so I can just write dt. And that's an easier integral than the original one. And that's what you get out of doing this substitution, that you get a new integral that's easier to solve. And what it says here is, can you find all functions that, if you differentiate them with respect to t, become square root t? The easiest way to answer that is to start by rewriting it to t raised to the power of 1/2. And taking the square root of something is the same as raising it to the power of 1/2. And then I can finish the calculation. When we integrate, we don't subtract 1 from the exponent. We add 1 to the exponent when it's a power function. So here I add 1 to 1/2. 1.5 added together gives 1.5, and 1.5 is the same as 3/2. And here in front, you must remember and write 1 divided by the new exponent. So you must say 1 divided by 3/2 when integrating.
And then there will be some constant of integration.
Ouch, it's reciprocal. And here are 3/2, which is 2/3. So when I say a division with a fraction, it flips the fraction upside down. So I get 2/3 times t raised to the power of 3/2 plus k. And finally, I can replace t back in t's place and do a reverse substitution. So I take what's with t and put it back in t's place there, ending with the final result of 2/3.
Times parenthesis 1 quarter x to the fourth.
Remember 2. It's raised to an exponent of 3.5 and then plus k. And k is some arbitrary constant. So we'll write it like this, that k belongs to the set of real numbers, and here is the result. So that was exercise 11. Now let's take exercise 10.
In exercise 10, it says,
the integral of osnus to x to the negative 1. And then it's multiplied by negative x to the power of negative 2. Like this. It's not like that. And again, it's an integration problem involving substitutions, indicating a kind of family. And what does that family consist of? Well, the family consists of the fact that if you differentiate x to the negative 1, you get exactly negative x to the negative 2. You can just try it. If I bring down the exponent and subtract 1 from it, I get negative 1 times x raised to 1 less than -1 must be -2. So we can see that there, it corresponds to writing g prime, if this is g and this is f. So we have an integral called f acting on g multiplied by g differentiated. And when it's this kind of integral, you can perform a substitution. You might remember it from last time. It looked like this if you write it out. If you have a function f acting on a function g, and you're so lucky that it's also multiplied by g differentiated. Well then, you can solve it just by finding an antiderivative for f and let it act on g untouched, like this. Because that is an antiderivative of f, and it's g unprimed. And we can just do that here. So all I need to do is find an antiderivative of cosine. And what's the function that, when differentiated, gives cosine? Well, that's sine.
So this integral must give sine
to g unprimed, and g unprimed is then x first. And then plus k.
So this is the answer.
And d integral. Any questions?
If not, we'll start
Lovely.
up 12.
And it says the integral of the exponent.
Plus 7x, all of it is
Electricity.
raised to the power of Rasa.
And here I can see that when I did the task, I ended up making a mistake. These
I'm
ones
stuck with
sitting
it, and not
both
because
them.
I have a good reason.
And this task I could solve, but I just don't feel like it. And what do I mean by that? Well, taking something and putting it in cells, it means taking it and multiplying it by itself until there are 6 identical factors. And then you can start multiplying it out.
With that one, that one, with that one.
That one with that one, that one with that one, all the way through. And then you end up with a 12th degree polynomial. And then you can integrate term by term. And that wasn't what I intended for you to do. And then I found the task. Because what I intended was just to have this differentiated, which made the task much easier. Because then it's direct. So I just forgot about it in the rush there. And what does x squared differentiated give? It gives 2x. And 7x differentiated, it gives 7. So I forgot to write this down that I just had to multiply by, because then I knew that it would be the task. Nice and easy, because then you can use the substitution method. So let's try to solve it now that I've turned the task into one that's not so focused. Because what we discover is that if you differentiate this, you get that. So I set that to t and make my substitution. So that's the start of the thought process.
I call tx squared plus 7x.
Then I differentiate
With
t
respect
to x and multiply dx on the other side. So I'll just skip a step and find dt.
So that takes
It
today
must be the differentiated plus the differentiated. That's 2x.
plus 7.
And now we can
Parentheses
see
to d.
that's exactly what's written here. So 2x plus 7 times dx, where I forgot to write in this factor, that was supposed to make it easy for the discoverer, can be replaced by dt. So what is now in our integral? Well, it's actually the integral of t to the 6th.
T to the 6th date.
And that is an easy integral.
Because you just have to increase the exponent.
So you go up to 7. And then remember to say 1 divided by that new exponent in front here. That's how you integrate a power function. And then plus k. And finally, I can do the reverse substitution. So now I take what t was, x
Plus
squared.
7x, and plug it back into the t spot there. And then it's done.
So the answer becomes 1/7
Times 6
Again to the 7th power.
raised to the 7th. And then plus k. Voila, it's actually solved. And let's just pause for a moment and think. What is it exactly that we've discovered? What is this?
It is all the antiderivatives for that.
For what exactly is that? The integrand. The integrand is everything that comes after the integral sign. and stops just before the symbol dx. And we can just quickly check in our head. Does this make sense if I differentiate this? Then I get the integrand. How do I differentiate a 7 times something to the 7th? Well, the 7th stays, and differentiating something to the 7th gives 7 times that something to the 6th. So 7 times the 7th gives 1, and I get that something to the 6th. But I'm not finished differentiating, because it's a composite function, so I must remember to differentiate the inside, which gives 2x plus 7, and multiply that on. And we see it's exactly what's written here. So everything adds up. So that was problem 12. Then came problem 13. And I had warned that problem 13 was a bit difficult if you didn't have a good idea. Because here you're supposed to integrate the natural logarithm of x. And typically you might be completely blank and think, how could I even guess what the antiderivative is for that? And then there was someone, it wasn't me, but someone else who was creative and thought, I can just write a 1 here, multiplied by it.
Why is that clever? Well, it turns out to be clever.
There are 2 functions multiplied together, so you can use integration by parts. The question is, which one do I differentiate? And which one do I find an antiderivative for? Let's try to call that one f, and this one g. And then we use this rule. Capital F times g minus the integral of capital F times g prime. That was the rule we had last time, called integration by parts. Let's try using it. Let's see what we get out of it. First, I need to find an antiderivative for f. What is an antiderivative for 1 dx? And x doesn't really differentiate here. Then I have to multiply with g unchanged. And g was ln x. So I'll do that. So now I've reached this point. Now I need to write a minus, because that's what the rule says. So I write a minus and a new integral sign, and then I find the antiderivative again for 1, which is again x. And this time I need to deal with the constant. So now I have to differentiate ln x.
But that gives an extra part.
And now we can solve it completely. Here I am done, so I can just copy paste it. And here it says the integral of the 1, because the extras cancel out.
And what is the integral of 1? It's just x.
Also with the constant factor.
And then we are done. Here are all the antiderivatives.
Here are all the antiderivatives for ln x. Does it match then that if you differentiate that, you get ln x? It should. So just for fun, we can do a little check calculation. A check. We'll check that if it really is true, then you should be able to differentiate that and get ln x. Let's give it a try. Let's try to differentiate. Look here, x or x. I can drop the constant because I know it gives 0 when you differentiate. Just notice how nice it sounds when you say it. That's how you remember it. I see it sounds like a drum, a rhythm, or an X or XX. Can you feel it? That makes it easier to remember. Let's try differentiating X or an XX. If I have to differentiate X to an XX, then I first need to differentiate a product and then a difference. So I start by differentiating the product. I use rule number 3. Differentiate the first, multiply by the second untouched, plus the first untouched, multiply by the second differentiated. X differentiated gives 1 times or an X untouched, plus X untouched times or an X differentiated, which gives an X denominator. Differentiate then X, it gives 1. And X cancels with X, so you have 1 minus 1. That also cancels. So the whole thing just gives ln x. Sweet. So here are the antiderivatives for ln x.
That is ln x.
Differentiate it, and I'll get it next. So that was tiring.
Now we only have task 15 left.
So we went through all the tasks from last time, and it's called the integral of x plus 2 over
X squared plus 4 minus 6 dx.
And then here you might feel a bit uneasy when you first see it, because it's the first thing you learn in math class when you're looking for a family. Is there a family? if I differentiate the denominator, I try the numerator. Let's try. X squared. Differentiated gives 2x, 4x differentiated gives 4, 6 differentiated gives 0. So the denominator differentiated doesn't give the numerator.
You think about the next numerator.
And sometimes almost is good enough. So when is almost good enough? Almost is good enough if it works, except for a constant you just need to multiply by. Try to see it for yourself. Now I'm trying to show you x squared differentiated gives 2x, but I don't have 2x. I only have 1x. And 4x differentiated gives 4, but I don't have 4. I only have 2. But you can see if you multiply the numerator by 2, it would work out. So you just start a thought box and set t equal to what the differentiation almost gives the other.
Remember, you have to add in with it.
So I said t equal to x squared plus 4x minus 6. And now I can find dt dx. It gives 2x plus 2.
And then I multiply the dx over to the other side of the equal sign at once.
Oh, sorry, plus 4.
Plus 4 this year.
But I don't want 2x plus 4. I would much rather have x plus 2. So what do? I multiply the equation by 1/2. So if I just multiply the equation by 1/2, it says that 1/2 dt is 1/2. And then I have to multiply by 1/2 here. That gives x. So I have to multiply by 1/2 here. That gives 2. And now the thought box is over. Because now I can see that x plus 2 in parentheses. That's what? Times it is x. Matches what's written here. So what's inside this bubble can be replaced with 1/2 dt. This here. 1/2 dt.
dt. And down here, that's what I had replaced with t.
So what does it say now when I perform my substitution? It says the integral of 1/2 dt over t. But the half, that's a constant that's multiplied and goes outside the integral, because that was one of our integration rules. And here there's a hidden one left. So it actually says the integral of 1 over t. And then I can move dt down in front of the fraction, because you can deal with a fraction by multiplying up in the numerator. So you must also remove it from the numerator and move it down in front. And now you can see it. Because what is the function that differentiates giving 1 over t? It's the natural logarithm of ct. So the answer to the whole task is, sorry, I'm getting a bit of a confusing blackboard here.
It becomes 1/2.
Times the natural logarithm of the absolute value of t, where t was x squared.
It's 4x minus 6 at the end plus k.
And here's the answer.
So that was the last problem.
You can see that to integrate, you should ideally be good at differentiating pretty much anything in your head, because otherwise it's hopeless to figure it out.
It helps a lot if you practice differentiating.
Are there any questions about these problems?
Now I will pause. Otherwise, I'll take this opportunity to welcome you to Mathematics 1, because it starts now. So far, we've only reviewed things you might have heard about once. Maybe a long time ago, maybe not so long ago. Now we will start with the syllabus. So we'll also need to start doing more at home, like solving some problems for practice and such. And if there's anything from before that's been difficult for you too, I would recommend watching the videos again and trying the exercises again, preferably as soon as possible. If you can spend an hour now and then in the evening watching the videos again and doing some of the exercises, then do it. Otherwise, we will now start with the first topic, which is a relatively big topic in our curriculum, complex numbers. So we're starting on that now.
Thank
It's
you.
brilliant to take notes and ask questions all you want, because as you'll discover, a really cool way to learn math is by playing your way to understanding it, by talking to others about it. So talk about complex numbers with everyone you meet from now on until it clicks. At home, tell your mom and cat and partner and boyfriend and so on.
Complex to grasp.
It's really amazing.
Incredible to discuss complex things. Let's get started.
And for those of you taking pictures of the boards, I'll try to remember to number the boards from now on, because we're now covering the curriculum. So let me quickly number this one. It's the first one. So that's that board.
I could undoubtedly mess that up.
So the topic is complex numbers. So the first question that pops up is, in any thinking person's mind, what are numbers? Because if I'm going to understand some new numbers called complex numbers, it's good to start by thinking what exactly are numbers. So let's just consider for a moment, what are numbers? What are numbers? And then you'll realize, if you ask yourself that question, that there's no question in mathematics more fundamental than that.
Because if you're going to do calculus, you need to learn about functions. You'll have to learn about functions.
You'll need to learn about variables and coordinate systems. And to learn about those, you need to learn about numbers. There's no topic in mathematics that ultimately doesn't boil down to understanding numbers. So actually, this is the toughest question, because everything relies on it. And maybe nobody really knows what a number is. It's a mental abstraction. Someone just came up with it. But there is a good way to think about numbers. At least one we can use in this course. A really good way to think about a number is as a place. So you can think of a number in two ways in this course. And both ways can be visualized in different situations. One way is to think of a number as a place. And another way to think of a number is that it can be perceived as an operation. Like something happening, something going on. So let's talk a bit about numbers as a place, so we can see what he means by that. Imagine you have a straight line here, equipped with an arrow. We call this a number line.
And on this number line, I can choose any random spot
And call it 0. And then I can imagine that numbers to the right of that chosen 0, that's positive numbers. Numbers to the left of that 0 share are the negative numbers. And numbers to the left of that 0 are the negative numbers.
Those are negative numbers. So here we have the positive numbers.
And over here, we have the negative numbers. So what is a number?
It's the place.
To me, that place is associated, connected with a number. It could be the number 1, for example. And then it could be that if I went just as far again, a new place appears, which I identify with the number 2.
So a good way to think about numbers is that a number is a spot on a line.
A one-dimensional
Line, a number.
But you can also think about numbers as an operation.
Let's try to think about the number -1 for a moment. What happens if I take -1 and multiply it by 2?
-1 times 2 equals -2.
So now we can ask ourselves, what happened to the number twice?
When I multiplied it by -1. So if this here is 2, what happened to the 2 when I multiplied it by -1? It flipped over here. So you could think about it as if you had a rod hinged at the 0 point, and the rod extends to the 2, then you swing it around 180 degrees that way. So the tip of the rod lands here at -2. So one way to think about the number -1 is that -1 is a 180-degree rotator under multiplication. It sounds fancy, but it's really not. -1 is a number that can make things rotate 180 degrees if you multiply by -1.
So that's the way to
Think
do
of
it.
the number -1 as -1 being perceived
as a 180-degree rotator.
180-degree rotator.
Ends in the song called Rotator with Disney's Lizzie.
It's a good track. If you don't know it, you should go home and listen to it. But you can think of -1 as a 180-degree rotator. Like on the multiply by thing, it rotates 180 degrees. Try to see for yourself. What if 2 details were lying here? It's called -1. What happens if I take -1 and multiply it by -1? Well, -1 times -1 gives +1. So again, we've rotated 180 degrees. No matter what number you multiply by -1, it rotates 180 degrees off the number line and lands back on the number line somewhere else. And it turns out to be an incredibly cool way to think about -1, because soon you'll learn something called the imaginary unit. And that's not a 180-degree rotator, it's a 90-degree rotator. So it's just a new number that can do something different. -1 can make things rotate 180 degrees. However, the imaginary unit I, which you'll hear about in a moment, can make this rotate 90 degrees when multiplied. And you need that because you'd want to be able to rotate in all sorts of angles, not just 180 degrees. Also 90, 45, 10.5, 10 quarters, and so on. So you can think of a scenario.
Numbers like a point on a line.
If it's my real number, then it's somewhere on a line. But you can also think of a number as something that does something when you multiply by it. Or as something that does something when you add, subtract, or divide by it. Both ways of thinking about a number are equally valid, but it depends on the situation you're in, which one you choose, which method you choose to think of a number. So how many different types of numbers have we encountered so far? Let's start by talking about them here. These are called the natural numbers, and that's probably the first thing humans invented. The natural numbers. And what are those numbers? Well, they're the numbers 1, 2, 3, and so on.
So they're all the positive whole numbers.
Are they positive in the same spot? And what can you do with them? What can you do with such natural numbers? Well, you can add them together. You can also multiply them. So we can add them. And we can multiply them. And can't we do anything else? Yes, we can. But if we do something else, we don't end up with natural numbers again. Can we subtract? Sometimes we can, sometimes we can't. For example, you can say 10 minus 3. That gives 7. Is 7 a natural number? Yes, that worked out well.
What if I say 3 minus 7?
Then I get -4. And -4 isn't one of the numbers, so it's not always possible to subtract and be sure that the result is in that number set. So you see, there are equations I can't solve if I only have natural numbers. So in order to solve those equations too, you expand the set of natural numbers to include negative numbers. Initially, you expand the number set just a bit, and you get this. Because what you're expanding to now is the set that includes all positive whole numbers above 0. Let's just check on your health status.
0, 10, 2.
Pull, and then you continue today.
But you also need negative numbers, because that way you can keep track of how much your neighbor
Or
owes.
1 potato or 1 apple or whatever the person pretends to borrow.
And here we talk about the set of numbers C, which comes from Zahlen, meaning numbers in German. And these are the following numbers. It's the number 0, and the number 1, and the number -1, and the number 2, and the number -2, and so on. So that's all the whole numbers, both 0 and the negative whole numbers. And what can you do here? Well, you can combine numbers, then you land on a new Z. If you combine 2 numbers from Z, you land in Z again. You can subtract 2 numbers from each other, any 2, and you stay in Z. You can multiply 2 numbers together, and you stay in C.
Watch it again.
But you can't divide the 2 numbers with each other and necessarily stay in Z. Because if I take the number 3 and divide it by the number 2, I get 3 halves, which is 1.5. And 1.5 is not in Z. So that means this equation here, 2x equals 3, can it be solved? Yes, everyone knows that this equation has the solution 1.5, and 2 times 1.5 equals 3. So does this equation belong to the physical world? Yes. Take a rope that is 3 meters long and decide to cut it in half with scissors. Just like that. Snip. Of course, you can cut a rope that is 3 meters long in half and get two pieces that are each 1.5 meters. So we need to be able to handle that equation, but we can't solve it if we only have a number that's in the set. Can you see there? Because the solution to this equation is that x equals 3.5, and 3.5 does not lie in the set of integers. So this is here to solve problems, like taking a rope that is 3 meters long, cutting it in the middle, and telling me how long each piece is. You need to extend the set of numbers once more. And now they've come up with something called Q. So maybe there's a set of numbers. So Q is it? It's the set of numbers that can be written as fractions. It's the set.
Are numbers.
That can be written some fractions.
So are we in Q?
And so the question is, can we solve all the equations we need there? Unfortunately not. We can solve more equations here with this set of numbers than we can with that. And we can solve more here than here, but there are equations we cannot solve here. And it was suddenly discovered in mathematics that problems out there in reality cannot be solved if you only have the set of numbers that can be written as a fraction. And it's kind of mind-blowing, because how many fractions can you choose from? Infinitely many. Always infinitely many. Imagine you have the number line here. I have a number, a, and let's say a can be written as a fraction. Here's another number, different from a, namely a number b. And let's say b can also be written as a fraction.
Then it can be managed.
Fractions in between here.
A plus b divided by 2.
That's right in the middle, also a fraction. Are there also some numbers on the number line between that and this? Yes, half it. Bam. There's also a fraction. How many fractions lie in between here? Infinitely many. So how is it possible that there are lines I can't solve?
Well, now she finally has many waves to choose from.
And here's an example of a problem that has a solution. We know that, says common sense. But the solution cannot be expressed in cubic terms. And imagine if the story goes like this. You have a square, and it has a majority. And so it is that the side length is 1. So there's 1 there and 1 there. And because it's a square, there are 90 degrees in the corners. And then someone says, now I've built such a square. I've stretched the string across the diagonal. How long is the string? Then an old Greek mathematician said that if you have a right triangle, then one leg squared plus the other leg squared gives the hypotenuse squared. So Pythagoras says this. One squared plus 1 squared equals the side you want to find, which I'll call x squared. But here is 1 and here is 1. That makes 2 together. So it says that to find a number, to find x, you need to find a number that squared gives 2. And it turns out that if you search in Q, even though there are infinitely many options in Q, none of them actually solve it. And you can prove that quite simply. There is not a single fraction in the entire universe that squared gives exactly 2. Does that mean there's no distance from here to there? Of course not. Everyone knows if you have a board that is 1 meter long and another board perpendicular that is 1 meter long, and you stretch a string between them, the string has some length that can be calculated. And the solution to the equation is that x equals the square root of 2. And if you ask a calculator, it says 1.4142 and then infinitely many decimals. And this number is a spooky number. Spooky in the sense that there's no fraction that's exactly right. And you can prove that really well.
So it's not feasible to only work in Q, and then we can't solve the problem.
And mathematics is intended and developed to solve problems in the world around us. So that's why we expanded the set once more to the set of real numbers.
So what is that?
Those are the real numbers.
And what kind of numbers are those? They're all the numbers you can almost imagine.
that you can think of coming up with, like regular people
So it's just all that.
and authorities' assistants. And what kind of numbers are these? They represent how many apples you have. So the number of apples you have at home, that's a real number.
These are called the real numbers.
It's also too many bananas you owe your neighbor. So those are also the negative integers. It's also the pieces of apples you can make with a knife by cutting it into pieces. So those are also all the fractions. They're also part of the real numbers. It's also all those numbers that can't be written as a fraction, but exist somewhere on the number line. These are the so-called irrational numbers, which can be written as a fraction, hence not ratio. It's called irrational in Danish. So the irrational numbers are also included here. So your debt in the bank, or if you have wealth, is included in the real numbers. Your apples, what you owe in apples, all the fractions, and everything that can't be written as fractions, it's all here. And now you might be thinking, how could I ever need more than this? Is this a complete number system? So that all operations I do within it produce results that remain within it.
But I swear it's not.
What can you do in there to stay within it? Can you add numbers together? Yes. All the addition sums you can do with numbers end up creating a new number, which also exists within you.
All the subtraction sums you do.
The same goes for multiplication. The same goes for division. But I can't say the same for root extraction. Because it turns out that before you know it, problems from the real world emerge. These aren't just imaginary. They come from the real world that can't be solved here. This means mathematicians were forced to expand once again. And this is where it gets exciting. This is when you can expect those goosebumps to show up with a sneaky creeping arm. Because the numbers that emerge now are nothing short of genius, because they're invented to solve those problems out there. At least, but the numbers seem a bit spooky because you only encounter them late in your education. You'll just have to get used to them. And these are called complex numbers. So this equation here, x squared equals -1, it doesn't have a solution. There exists.
So it's not a real number that squared gives -1.
So we can't omit
Bravo, negative
troublemakers.
quarters. And then I can be someone who's on, for heaven's sake. Should we also do that? I've never needed to extract a negative square.
But it
I think that's
turns
nonsense.
out more.
Complicate things in the world around us, like quantum mechanics. Introduce the complex
It's
ones
not that talked about.
and the probability of finding a particle in our universe in 3D space with time. The probability is described by a function that includes the imaginary unit, which is a complex number in a Hilbert space, which is complex in n dimensions. Crazy stuff, I mean. So why do we need to learn about complex numbers? Because it turns out you need them. As long as I'm laid back and enjoy the fact that they are complex numbers, sometimes you think you'll never use them, and it's not certain. But if you're going to study further and become a civil engineer and maybe research one day, you might very well come across complex numbers. And there are many calculations you'll encounter that use complex numbers where it's important to know them. So we expand the number ranges once more. So here comes
Talk about whether
its
they're
own
complex,
set.
and you write them like this, and put them
Notice
on
that all our sets of numbers are written with a double line. It's called being written in.
a written set, a written Q, a written R, and a written C. So these are the complex numbers.
And now, so of course, there are some whose minds immediately need defense that there is a complex number. And we'll quickly hear that a complex number can either be perceived as a complex number,
Place or some geometric operation, for example, something that rotates something else.
So let's now introduce the complex number on board number 2, where it will make sense. In this picture first, To understand complex numbers, let's just recap what was a real number.
A good helper tool. Here's a place.
On the number line.
So here is an example of a real number.
0 is a real number.
Here is a positive real number. Here is a negative real number. So those are real numbers. They can all be thought of as points on the number line.
Yeah. So what are complex numbers?
Does anyone know that? When are you going to say it?
So a complex number is not just a point on the number line, it's a spot in the two-dimensional number plane.
So we can write that in a complex number.
Yes. Instead,
in its
two-dimensional number plane. And this number plane has been called
extensively. So just remember to mention one of the big heavy math guys, Gauss. So instead of saying the complex number plane, it's typically called the Gauss plane. But what have I actually said? I've said that a regular number, as you know, is a point on a line. The new numbers we're about to learn about, they're a point on a plane. So you simply draw a plane, just like you learned in elementary school, and it's a rectangular coordinate system. And every point in this entire plan, it's now a number. So here's a number.
Here's another number, but it's actually a real number.
Here's another number, but it's actually a purely imaginary number.
Okay, so what is
a complex number? Is any point in the two-dimensional plane. It's a complex number. It's 1, it's 1, it's 1, it's 1. There are infinitely many. If it happens to land on the x-axis, then it's a real number. So a real number is also a complex number. It's just a very special, simple, complex number. If it happens to land on the y-axis, then it's what we call a purely imaginary number, but it's also a complex number. So all numbers in the entire plane are complex, and some of them are purely real, some of them are purely imaginary.
And complex numbers are written with the symbol Z.
And this is my x-axis, as you're used to, and this is my y-axis. And if you just go from the complex number in the plane with a dashed line down until you hit the x-axis,
with the number here, I can call A.
And if you do the same until you meet the y-axis, you'll get a number here. I'll call it B. So how do I tell my neighbor that I'm standing there in that complex number? Well, one way to do it is just to tell my neighbor how far I've gone along the x-axis, A, and how far up the y-axis, B. And if I give him both A and B, we say I've given my neighbor an ordered pair of numbers. A pair of numbers means there are two numbers, and ordered means it's not the same which number you say first. You must say the x number before you say the y number. And it's written that the complex number can be written as an ordered pair of numbers. Parenthesis A, A. So this is a complex number. So you might say there are two numbers. Yes, but those two numbers together point to one spot in the plane and only one spot. Therefore, they point to a very specific complex location, and that's a number. So even though there are two numbers here, you should think of this as just one complex number. Some say it's not the same as what we've learned in vector calculus. You could draw a vector from there, David. Couldn't you, Jim? Yes, I could. Bang. Now I've drawn a vector.
But a vector is not the same as a complex number.
It's not. But this is a position vector for the complex number set because it points to the spot where the number is. So a two-dimensional vector is very closely related to complex numbers, but it's not the same. Otherwise, we wouldn't have invented two different words for it. So this is a spade vector.
And action.
But the vector is not the number. The place, on the other hand, is the number.
This here is CFK.
Here is the position vector for C. They are two different things, two different mathematical objects. Just 10 more minutes, and then we'll take a break.
So a complex number, what is it?
A complex sail.
An ordered pair of numbers.
On the plane, that means two dimensions. So you could say a complex number is a two-dimensional number. A real number is a one-dimensional number. So now that we know what a complex number is, it's a place on the plane. We can introduce rules for calculating with complex numbers. So now comes a subheading to the main headline called calculation rules.
Oh,
we now need two complex numbers.
Complex numbers. Let's call the first complex number Z1.
And its name is AB. This means it goes out on the x-axis and B up on the y-axis. And then I have another complex number Z2 called CD. So now I can define what I mean if I want to add them or subtract them.
So here I am now defining a rule for sum.
And difference. So that means now I'm adding or subtracting.
And it looks like this. Number A, B.
Plus or minus, depending on whether you're adding or subtracting.
C, D. Add them together.
A plus or minus C, depending on what it says, this becomes the new first coordinate, and then B plus or minus D. That's how you do it. So the simplest way you can imagine adding two complex numbers together is the right one. You add the first coordinates together, you add the second coordinates together. That's it. And the simplest way to imagine subtracting two complex numbers from each other is also the right one. You subtract the first coordinates, A minus C, and you subtract the second coordinates, B minus D. And then you get that.
Let's put a frame around this because it's a bit important from here on.
And know how you did it. Listen up. Now we can actually make a discovery. So here we can
Thanks,
discover
that was
it.
good.
What happens if I add two complex numbers together, both having a y coordinate of 0?
So I'll take the number off. And then I'll add it to another complex number.
By looking, someone's coming.
What do I get then?
Well, suddenly,
I change in it.
when I have to say the sudden, it's right there by the rule. I get a new compile.
Both number called a plus C.
And 0 plus 0.
First there was 0 here.
So you can see that if I add two complex numbers that have 0 in the second place, I get a new complex number that also has 0 in the second place. And a complex number that has 0 in the second place is called a pure real number. So that's actually just something you might as well think of as quite good old regular real A. And this here I can think of as a good old fashioned C.
And this I can think of as,
so you can see that the complex numbers include the real numbers, because a normal real number added to another real number just gives A plus C. We know that from regular numbers. So the complex numbers include the real ones. How is that? Well, it's just all the complex numbers that have a y coordinate of 0. They are the real numbers. It was really cool that you discovered that. Now we need to introduce one more calculation rule before we can make the next discovery. We need a calculation rule for how to do multiplications. And that's new. There's no such thing as multiplying two vectors, but there is something called multiplying two complex numbers. But you can't multiply vectors.
You can't. You can scale and multiply them.
And you can cross them with actual multiplication. But you can multiply complex numbers, and that's why complex numbers aren't the same as two-dimensional vectors.
So how do you multiply two complex
I have a rule,
numbers?
and I apologize for it in advance because it might seem odd. But afterward, you'll realize there was no other choice. If it was all going to work, you had to choose what I'm choosing now. What comes next is called a definition. It's just how one has chosen to multiply complex numbers. Why was this chosen? We'll discuss that a bit later. Why was it picked?
So if I have a complex number called AB, then it moves A out and B up.
And I need to multiply it by another complex number called CD.
So you have to do the following. Sorry. In the middle of the screen, you have to say this times this, minus this times this.
Let's see.
Minus b times d. Then write comma, because now comes the second coordinate. Then you have to say this times this plus this times this.
So A times D, gang.
Remember B, gang, to watch.
And don't
Just
try
rinse
to memorize that by heart.
Because you'll never need to know it unless you're teaching math. Soon we'll discover that it's much smarter to do something else than to try to memorize that.
It says here how to multiply two complex numbers, and we'll find out the consequence of doing it this way. And if you really think hard about it, you'll realize you had no choice. You had to define it this way if you wanted to use complex numbers for what you intended to. So don't try to memorize that out. Okay, you don't even have to do it. It's almost like nonsense that just sits there. But this can easily be misunderstood. I had to sit down and look at it for my class because I always forget that rule. Just so you don't think I can do it without help. I can't. And right now, because I've just looked at it. But otherwise I can't. So what can we discover? Now we can discover something.
Now comes the chills, I hope, because I can explain it properly.
If you're getting tired, try to
Stay
list
awake
it.
now and listen to this. A cool discovery is coming up.
And after that discovery, we'll take a break.
Let's see what happens if you take a very specific complex number and multiply it by itself using this rule. So here comes a very specific complex number.
Is it a complex number?
You need to go 0 out on the x-axis and then go 1 up on the y-axis. So where is it located?
It's located here.
If this distance here is 1, then the number I'm talking about right now is located there. That's the number I'm dealing with. Is it a complex number? Yes, it is. Is it a very specific complex number? Yes. It's purely imaginary because it's on the y-axis. Let's see what happens if I take this purely imaginary number and multiply it by itself.
That's the test I'm doing. And then I use the calculation rule over here if I want to get some code.
What did it say then? That times that, minus that times that. So it starts with that times that, minus that times that, that times that, minus that times that.
That times that is 0 times 0, which is 0.
That times that is 1 times 1, but I need to remember to write it down. So I get -1. Got it? As the first coordinate. So I said that times that, minus that times that, it must give -1. Then I need to write the y coordinate. Now I need to say that times that, plus that times that. This is an easy 0, because I'm dealing with 0, and 0, because I'm dealing with 0. So it gives 0. But I just discovered something, right?
A complex number where there's a 0 in the placeholder? What was that number?
It was just a plain real number. So I might as well write it as -1. This is the good old number, -1, that we all know, which is over here. In -1, so try to notice what happened in this discovery. I found a number that, when multiplied by itself, gives the number
CQ.
So we have solved our problem. We have solved
The
our problem.
equation x squared.
Right, but
You will now see. We couldn't solve this equation before today.
Now it's solved. Here is the solution. This number is the solution to that one similar equation.
And from there,
because that number can give us so many chills.
so it's probably because it plays a very special role in the universe.
And deep inside ourselves, we give the number a name. We baptize it.
And we better put a box around that.
It's this complex number, which happens to be purely imaginary because it's on the y-axis. It's called 0.1. And if we define that number as I, it means it's something you choose. So we have now just proven that I squared equals -1. So the way I've presented complex numbers, I've proven that I squared is -1.
I haven't defined it. I've proven it.
And if you look in your math book, that thick one there, the story starts here, skipping everything before. So the part of the story that was over here is the proper mathematician's way to do it. But your book is written for engineers, so they start here, and therefore you don't stumble, because they just say, accept that something we call I squared gives -1.
So I thought, how could I understand it? Just accept it.
So what you need to understand is something completely different. You need to accept that it has turned out to be a good idea to look for numbers above and below the number line in the plane. And if you look there and introduce a number as something that's not one-dimensional but two-dimensional, you discover this. You simply discover that this number I, if you multiply it by itself, you get -1 if you accept that. That can also feel wildly strange, but it turns out that if you study mathematics, you couldn't define multiplication any other way if you wanted the rules to
Thanks
hold.
for thinking about it.
So that was part number 2. And in just a moment, we'll have a break. But for now, we'll have learned what a complex number is at a point in the plan. It can also be viewed as a geometric operation, as we'll see in a bit, and it can be used to solve Schrödinger's wave equation and quantum mechanics, which can tell us what it is.
What is the probability of finding a particle
in the universe.
If you look for it. So we need it not only if you want to learn quantum mechanics, but also if you want to learn oscillation theory, things that oscillate, and almost everything does, both in chemistry and mechanical engineering. Almost everything oscillates. You need complex numbers. So let's say we take a 10-minute break. So what would that be? 2 minutes past the half point or something? 3 minutes past the half?
and then we'll start again.
Have a good break.
Okay, I hope you had a good break. We are now going to make discovery number 3. I wonder what happens if you take a complex number called 0. What kind of complex number is that? It's a complex number where the first coordinate is 0 and the second coordinate is not 0. That means it's a number that lies on the y-axis. That means it's what we call a purely imaginary number.
Yeah.
Can it be written another way, that number there? We'd like to discover if it can be. So let's try taking a number called B0. That's purely a real number. It's purely imaginary. I'll just write it here. Pure.
Imaginary, that's what they call it.
Then comes the English word imaginary. When you kind of imagine that there are numbers above and below the number line,
and this is purely real. And what we'd like to discover is what happens if you take a purely real number and multiply it by this special number called A. So let's try to find that out. I take a purely real number B, 0, and then I multiply it by I, which is called 0, 1. Do you remember that? That was I this here. It was that number that behaved so specially that it got its very own name. We call it IK. Now, how was it you multiplied? You said this times that minus this times that. So we can start by doing that. This times that is 0 because I'm dealing with 0. Minus this times that is also 0 because I'm dealing with 0. So that gives 0. Then I should say this times that. Now this times that. This times that gives B, and this times that gives something. So it just gives B. That means if I take a pure real number, which is that B0 as it stands here, this here was purely real, and multiply it by I. Now I get a clean one. You feel the closeness.
So you can see these two symbols here, they just switch places. When you multiply by ik, we'll interpret that with a drawing so you can see it. Let's just draw what's in this line,
Because it's always much easier to understand when there's a drawing.
So here's the plan view between the x-axis and the y-axis. And we start by drawing the detail called B0. It could be that it's here. So here's B. And it doesn't go up the y-axis. So it's right there. It's a purely real number. And then I multiply by I. And to see what happens when I multiply by I end up in 0, B. Where is that located? That means this number here, what has it done? It's just rotated 90 degrees. Can you see it? If we imagine there's a pole here, hinged out here, we're about to lift it up. So you can see, you rotate that number, we multiply by I by 90 degrees. Up here now is the number 0, B. So this is the number 0, B. And the distance here is B. And that number is purely imaginary.
So what we can
Just
see
annihilate
is
that the number I is a 90s rotator. If you multiply by I, then what you multiply with I rotates 90 degrees. Which way? That way.
and this direction I call math up.
Positive circulation direction.
This way. When the cod moves, it goes positively this way. But that's not how mathematicians think about positive. They think this is positive. Why? Because you go from the first to the second to the third to the fourth quadrant. So when the quadrant number increases, it's positive, say the mathematicians. So it's positive. So now we can talk about I, the number I, which was the number 0.1.
Yeah.
A 90-degree turn. And take a step. Under multiplication. And that's an important discovery, because suddenly you can see things as operations in the plane, instead of just some abstract, weird math. It's just something you can see. You can actually see it happen. And with this, we can make a new discovery. What we've got here will be discovery 4, probably the most important one. So here comes discovery 4. What is our discovery? Well, I'd like to see if I could invent a whole new way of writing complex numbers. So here's a complex number. What's that complex number? It's the complex number that goes A out on the x-axis and B up on the y-axis. Can it be written in a new way with all our discoveries? Yes, it can. Let's see. Because it can be written like this. It definitely can, because we've established the rule for how to add complex numbers. And it says, if you want to add the complex number with the complex number, you need to do this plus this, which gives A, and this plus this, which gives B, and then you get that.
So that's definitely something we can do. Hello to everyone online.
But what we also know is that when it shows 0 in second place, it's definitely a real number.
It can simply be written as an old-fashioned A.
That's a number right there. I don't even need to write 0, because I know that if it shows 0 there, it's real. But what can that number do? How can I write it? Oh, right. It's over here. 0, B can be written as B, 0. So that's what I'll do. So here I write it as, instead of 0, B, I write B, 0. And then you multiply. Because I just saw that if you take B, 0 and multiply by 0, 1, multiply the two complex numbers, you get 0, B. I showed that here. In discovery 3, but now I can think further, because here it stood out. And what kind of number is that? But it's just a good old B. It simply says B here. And what number is that? It's the number I. And now I've come up with a completely new way to write a complex number.
These are complex numbers that go out of
And
use
ask, how can it also be written?
as A plus B times E.
That's cool. And why is it cool? Because now we can calculate with complex numbers, just like the good old regular numbers. The only thing we need to know is that I squared is -1. So you can precisely forget everything else I said. You only need to hear it once. Everything else I said was just to lead up to this. A complex number z
Can always be written
as a real number a plus a real number b times the imaginary unit. Any complex number can always be written like that. And it turns out to be the way to do it, because it makes it much easier to multiply and divide, add and subtract complex numbers by writing it like this. So the story of ordered pairs of numbers is what a mathematician is interested in, and he does it to be able to teach it. But everyone who uses complex numbers starts here. And then it says, the only thing you need to know is that a complex number called a plus b times I, where I squared, is -1. And that's where I start in my textbook. Where I squared equals -1. So now we can start solving problems. We can start practicing working with complex numbers. Let me just solve a couple of problems for you. Then I'll set up a line for you to try solving. And Mikkel and I will walk around to help. So here comes example 1. I am just making up a problem. Set one from some complex number I'm coming up with right now. And it's called plus 3i. So someone might ask, why do you write 3i? I've seen people write I times 3, putting the I before the 3. Well, the factor order doesn't matter. So whether you write 3i or I3, you can decide. But it turns out it's smartest to write the number first, and then the I. When you're dealing with numbers, but when you're dealing with very large symbolic expressions, it's smartest to do it the other way around. We'll get to that later in the course. So when I write with numbers, I write 2 plus 3i. I don't write 2 plus I3. But when I'm dealing with large symbolic expressions, it's smart to write 2 plus I times whatever comes next that's related. So you see where the I is before the big ugly part comes. And it makes it easier to see what's real and what's imaginary. The total is called the real part of C1. So you write it like this. The real part of C1
is 2 in that number.
And in the imaginary part, the part of C1 is half with 3.
Notice there's a trick here.
And it's a question you might get in the oral exam. I say if they go to the oral exam and say, here's a complex number called 2 plus 3i, what is the real part? 2, says Christian. Then I ask, what is the imaginary part? And then Christian might say 3i. That's incorrect.
In the imaginary
That's a
part,
frustrating challenge.
it's only 3.
You can just forget about it. It's the I that indicates it's in the imaginary part, but it's only the number that's called the imaginary part. Just a little warning, so you don't answer that question wrong. Let me come up with another complex number, C2, which is called 5
minus 4.
The complex number 2 has a real part of 5 and an imaginary part of -5.
Plus 4. Not minus 4i.
Let's try to add the two complex numbers together. So let's find the sum and the difference. And see the connections. So what becomes C1 without C2? Well, thankfully, it's really easy. It's 2 plus 3i. 2 plus 3i. Which just needs to be added to 5 minus 4i. And now it's as easy as it gets. You just take the real parts first. 2 plus 5 is 7. And then I take the imaginary part out of the 3. Minus 4i, that's minus 1i.
So the result is 7 minus I.
So you just start by taking all the numbers that don't have anything to do with I and add them together. And then take all the ones that involve I and count how many bananas you have. 3 bananas minus 4 bananas. So I owe 1 banana. So it's as easy as it can be.
What if I need to find Z1?
Minus Z2. It's almost as easy. I start by writing Z1. It was 2 plus 3i minus And remember to put parentheses around it, because Z2 has 2 terms. And here it should say 5 minus 4i. And then it's just exactly how you learned to do algebra. I remove the minus parentheses and get 2 plus 3i. Minus 5, but then minus times minus equals plus. So I get plus 4i.
And then I do it like before. 2 minus 5.
I first take minus 3. And 3i plus 4i. That's 7i. And then I'm done. So the result is minus 3 plus 7i. So we have fun finding the product of the two complex numbers. And now you'll see. You don't need to remember that calculation rule that comes up. It's completely unnecessary. It's only if you're a math teacher that you'd bother learning it.
And I'm not even bothered. I always look at that
But
line.
let's try to find the product of Z1 and Z2. So what does it give then? Well, it gives 2 plus 3i multiplied by 5 minus 4i. And now you should look up at the board once, because here you're definitely going to mess up a bunch of times before you get it right. So let's do it together. What should I do? I have to say this 1 times that one, and that 1 times this one, again and again, just like you're used to in algebra. You multiply different terms with each other, every term in one quantity with every term in the other quantity. We also have to do that here. But there's a certain order that's smartest to do it in, so try to watch along. This 1 times that one, what does it give? So it's smart to say, once you've said this times that, then it's smart to say that times this. You don't usually do that. Normally you'd say this times that, and that times that. But now I first say this times that. Then I say that times this. Why? Now you'll see. It's because 3 times minus 4 gives minus 12. But I times I is I squared, which gives minus 1. And minus minus 12 is plus 12. So why did I do it that way? It's because now I've got everything that doesn't have to do with I first. This time I don't have anything to do with I. This one, and that one has a lot to do with I here. But because it's I squared, it disappears and doesn't have anything to do with I. Do you understand what I mean? 3i times minus 4i. If I just write it out, 3i times minus 4i, what does it give? Well, I start by taking the 3 times 4, that's 12. There's also a minus. Let me write this down. I times I, that's I squared. But I squared is negative 1, so I need to multiply by negative 1. Minus times minus gives plus, so that gives 12. That's why I wrote plus 12. Okay, yeah. Yes, every time you multiply 2 complex numbers in this form, you do this times that, and then this times that. And now you've got everything that is real. Just like that. Good. So you do this times this. That gives negative 8i. Here it says negative 4 times 2. It must be negative 8i. And then you do this times this. That gives 15i. And then we simplify it all. 10 plus 12 is 22. And 15 minus 8 should be 7. So plus 7i. And then we are done. We'll probably need to practice this a bit before we move on, just so we've worked through it. Does anyone have any questions? Yes, I'll just write down the tasks, which is you take the picture, the belief. Yes. So here's a little task for you to try out and have some fun with. We'll be walking around to help you if you get stuck. Tasks now. Okay, so here you have C1. It's 1i, and here you have C2. It is 3 plus 2i. And you need to find, yes, 1. Oh, determine. Set it. Plus Z1. All that times Z1. Run 2. That's correct. Minus 7. So there are 3. we see them 2 times Z1 minus 3 times Z2. All that concerns Z2. And we're going around to help you. So just try to see if you can get something. The task calculation is at your fingertips. And if you want, turn off the camera or pause the recording. Yes, now you have tried solving the tasks a bit. I hope it went well. We're working on these in class. Here is problem 1. I was supposed to say Z1 plus Z2. That's the whole times Z1. So here is Z1, here is Z2. And when all that is added together, it should be multiplied by Z1 again. Here we can see we get minus 1 plus 3. That's 2. And minus I plus 2I. That gives 1I. So 2 plus I should be multiplied by minus 1 minus I. So I say this times this first, which gives minus 2. Then I say this times this, which gives minus I times I, which is minus I squared. But I squared is minus 1. And minus minus 1 is plus 1. So I get minus 2 plus 1. Then I do this times this, which is minus 2I. And this times this, which is minus 1I. And minus 2I minus I is minus 3I. So all in all, I get minus 1 minus 3I here. And that answers the first problem. Problem 2. Here I have to calculate the difference, Z2 minus Z1. So here it says Z2 minus, here it says Z1. And this parenthesis is important. This parenthesis is unnecessary, but I've put it anyway just to emphasize that Z1 is here. Sorry, Z2. So what does it say now? 3 minus minus 1, that's 3 plus 1, so 3 plus 1. And so what that minus parenthesis does is that the minus becomes a plus, so it ends up saying plus I here. And that 3 plus 2I, I've just copy pasted it down, so I have 3 plus 1, that's 4, as a real part of 4, and 2I plus I, that's 3I, as an imaginary part of 3. The last problem was probably the easiest one to make mistakes in. You had to say 2C1 minus 3C2, all that times C2, and it states here. So I start by multiplying 2 into C1, then I multiply minus 3 into C2, and finally, I multiply all that by C2. When I multiply 2 in here, I get minus 2 minus 2I. When I multiply minus 3 in here, I get minus 9 minus 6I, and all that should be multiplied by 3 plus 2I, which is written there. This can be reduced to minus 11, minus 8, and now I need to multiply that by 3 plus 2I, and then I say, this times this is minus 33. Then I say this times this is minus 16, I squared, but I squared is minus 1, so it gives plus 16. So I say that at that point, it's minus 22I, and then it's minus 24I. And then I don't combine it. Here I get minus 17, and here I get minus 46E, and then we're done. Do you need a little break, or should I continue? Shall we continue a bit? We can, right? The next thing we need to learn is something called modulus and complex conjugates. You need that to divide complex numbers. So let's erase the board, and I've put the sponge, it's right there.
So now there's a new subheading coming
For
up.
the main heading called modulus. So if you have a complex plane, a Gaussian plane here. So earlier you saw that I called this the x-axis and this the y-axis. Usually we call this the x-axis, the real axis, and this the imaginary axis when talking about the complex plane. So now you'll see me begin to write re and im in those two places because I stand for them. And here's some random complex number, which I just want to tell you a bit about, which I call set. And it has so a number here I call A, and it has a number here I call B. And now we've just learned that C can be written as A plus E times B. And if I write in letters, I usually write A plus I times B. If I write in numbers, I write 2 plus 3i instead. But how you do it is up to you, because the order of the factors doesn't really matter. And this form here is called the rectangular form of a complex number. The reason it's called rectangular form, you can almost guess.
is because when you draw your complex number in the Gauss plane, it's like you've drawn a rectangle when you project the coordinates from this complex number set. So you can tell your neighbor where you are in the Gauss plane by first saying how far they should move out on the real axis, and then how far on the imaginary axis. And by drawing the corresponding rectangle, you locate where you are. And that's why we call it rectangular form. Now, one might ask how far it is from the origin out to the complex number C. That is, how long is the line from the origin out to C. And the length of this straight line connecting the origin with C is called the modulus of C. And you write vertical bars on each side of C, but you read it as modulus C. So this is modulus C.
And you can
As
think
it as a
about it
number.
next time.
Because it is also
What
called
also the numeric value is considered, and you can also call it the
Absolute value setting. So there are 3 ways to say it.
this is the same as the numerical value setting. And you can also call it the absolute value of Z.
But in this course, we use the word
Modulus. If you want to find the modulus of Z, you can use Pythagoras, because here it's a right triangle. And Pythagoras has taught us that a squared plus b squared equals c squared. So you can just write that down.
So we can use the calculations as well.
And when you calculate, we find that a squared plus b squared equals the length in the room. And how long it is, that's the modulus. So here you can actually find the modulus just by
the
taking
square roots on
Good
both
remote.
sides.
If we do that, then we have this formula. The modulus of a complex number C, what is it? It is the square root of a truffle into it plus the square of the imaginary part. That's how you find the modulus of a complex number.
And we put a little box around that because it was an important formula. And then we can, of course, just do a very simple example.
Example 1. Imagine you have a complex number called C1, which is 3 plus 4i.
It can be drawn. It's a complex number. So let's do that. Here's the Gauss plane, where this is the real axis and this is the imaginary axis.
The complex number goes 3 units out on the real axis. 1, 2, 3. So it's right there, we say, and 4 steps up. 1, 2, 3, 4. So it's here. And then we draw it in our rectangle. So here is set 1. That was a big number 1. Here is set 1. And now you might wonder, how far is it from Oreke to carry out? So how long is that connecting line there? Well, that's exactly what we mean when we say the modulus is set 1.
So what's the modulus of C1?
Well, we just plug it into the formula. Is the square root of a, the real part of set 1 squared, plus the imaginary part of set 1 squared. So that's the square root of a, 3 squared.
Plus 4 again.
Here we have 9. Here we have 16. 9 plus 16 is 25. And the square root of 25 is 5. So I made sure to choose numbers you can calculate, right? So it's a so-called 3, 4, 5 triangle, which nearly all craftsmen know. Because if you're out in the field and need to make a right angle, you just measure 3 meters one way, 4 meters the other way, and then adjust that point until it's 5 meters. Then you know that angle is 90 degrees. It's very clever. But what's called the modulus means how far away from the origin the complex number is. That's what it means. By the way, numerical and real numbers probably mean the same. If you write the numeric value of 3, what does that mean in Danish? It means how far is the number 3 from the origin. So if you draw a number line here where it's 0,
And here is the number 3. And I ask, how far is it from 0 to the number 3? Well, it's obviously 3. So the numeric value of 3 is 3. But if I ask, what is the numeric value of -2? So it's like asking, how far is it from -2, which is here? How far from there? Knowing that a distance can't be negative, so it's 2. So you can see that the numeric sign for real numbers is the exact same as the absolute value sign for complex numbers, which are like 2 vertical lines. That was one thing you needed to see. Now you need to learn something called complex conjugation, and it sounds difficult and complicated, but it's really not. It's super easy actually. So the next subheading is complex conjugation. So what is it? Well, imagine you have the complex plane here. It also sounds difficult when you first start here. So imagine a coordinate system, right? And in that coordinate system, you've pointed out some spot you call Z. That's a complex number. Here is our A, J. Larsen. Here is Imogen Eriksson. Now just mirror that position across the real axis. Just do it like this. And that number now lying there, that's a reflection. You mirrored that point over this mirror line. That number there, it's called its conjugate. And you just mark the conjugate by drawing a line over it. And you shouldn't draw a vector line over it. Don't do that. We aren't doing vector calculations. Just draw a simple line over it. And if now this complex number, if it's called a plus A times B, what do we know then? Well, then we know that the complex number is written in rectangular form, because this is indeed rectangular form. But we also know a bit more. We also know we have the number A here. And here we have the number B. Because this complex number has the real part A, and it has the imaginary part B. Remember, it doesn't have the imaginary part as B. It has the imaginary part B. What about this number down here, which is a mirror image? What real part does it have? Mainly, I can write that down. But note that the imaginary part
is just mirrored. So it's minus B.
Okay, because it's written
Is
here.
5. So here it's -5 because it is a mirror image.
So now it's cooled off.
Minus in action.
And that's what you call the complex conjugate element. So this here, the complex conjugate, what is it? It's a minus IB. And we put a bracket around it.
And what should I use it for then?
Z king you have become.
What should I use it for then? Well, everything the painters have invented can be used for something else they want to tell. So we can make some discoveries. What might happen if you multiply a set of complex numbers by its own conjugate? We just want to try it and see what happens. So what does Z times Z conjugate give? We could just calculate that. So let's try that.
Or what was it now? Z was, oh yes, A plus IB.
And it should be multiplied by Z conjugated with DIP. Oops, it's the sum of two numbers times the product of the same two numbers. That's what we transformed algebra for a couple of years ago. And the sum of two numbers times the product of the same two numbers, what did that give again? The first number squared minus the second number squared. Remember it. If you can't remember it, you just say 1 times 1, 1 times 1, 1 times 1, and so on, and you'll get it right. But if you remember one of our square equations, then it gives the first term squared.
Minus the second number squared.
But the second number contains an IE. And now you see what that gives. Because how do you square a product of two numbers? You do it by squaring both numbers. And what does that indicate to you? Right now you see 1. And minus minus gives plus, because there's already a minus there. So it becomes a squared plus b squared. And why does a mathematician get so excited when he sees that it results in a squared plus b squared? It's because he just discovered it, that it's raised to the second power, it's squared, you must now square it. So you take a complex number and multiply it by its conjugate. What does that give you? The modulus of that number squared. So everything that can be discovered should be discovered.
So it's just a discovery, but it's very cool.
Because you'll be able to use it for something in just a bit.
And this must be board number 4 here.
So in just a bit, when you're so confused by everything I've said, you're thinking, I can't take in any more new stuff. I'll pretend you're at an exam. And then I'll tell it all in exam speed, as if I were taking an exam in complex numbers. So you can see how you might do it if you get that question. There are 3 questions that deal with complex numbers in your exam questions. You can't explain it as thoroughly as I do when I'm teaching. So it's intense when you're in for the exam.
Okay, now let's take whiteboard number 5.
And see what we can use complex conjugation for. So what we need to understand is the next heading, which is called the reciprocal element. What does reciprocal mean?
Here is the number 3. Here is the reciprocal of 3. Here is the number 7. Here is the reciprocal of the number 7.
So the reciprocal element of a number, what kind of number is that? What kind of number is that? Yes, 1/3, that's the number you can multiply by 3 to get ones. What is 1/7 as a number? 1/7 is the number you can multiply by 7. So you got 1.
So what is the reciprocal of x?
The reciprocal of x is 1 over x. This is called the reciprocal of x, which means if you multiply it by x, you get 1. You could also call it the inverse of x, it's 1 over x. But we call it the reciprocal. And now we want to learn how to find the reciprocal of a given complex number. So we need to learn to find the reciprocal element, meaning the reciprocal complex number that corresponds to some given complex number. So I'd like to find 1 over z. I'd really like to find a formula to find the reciprocal of a complex number z. What kind of number is this? It's the complex number that if I multiply it by z gives 1.
And now we'll see where to find that one.
It needs to be found. That's what we've decided to do. It's kind of a little puzzle we've set for ourselves. We want to be able to find the reciprocal of any complex number. We actually need that. So here it comes.
And you find it as 1 over some complex number set.
Yeah, you get this great idea. You extend the fraction by the complex conjugate element. So you multiply the numerator by c conjugate, but then you also have to multiply the denominator by c conjugate. Where did that idea come from? I don't know. Someone had that great idea. Maybe because he already knew that c times c conjugate. What did that give again? Modulus c in. And that's what we looked at in the 6th half. So this can be written as z conjugate divided by modulus z. And that seems like gibberish, but now you'll see an example and it isn't. So let's try. Here's the key. Watch how it's done. Example. Here's a complex number called z, which is 2 plus 3i. I would like to find the reciprocal for that. So basically, I want to find a number which, when I multiply it by 2 plus 3 times I, gives me 1. That's what it means to find a reciprocal. So what's the reciprocal of the number 3? 1/3. Why? Because 3 times 1/3 gives 1. What's the reciprocal of 7? It's 1/7. Why? Because 7 times 1/7 gives 1. What's the reciprocal of 2 plus 3i? I don't know. But when I find it, it's a number that multiplied by 2 plus 3i gives 1.
Are you following? And I'm just trying to use the formula, although it seems to work.
So I want to find 1 divided by 2 plus 3i. So basically, I want to find the reciprocal of the number 2 plus 3i. What does the formula say to do? It says, can't you just multiply the numerator and denominator by the conjugate of z? So I do that. What's the conjugate of 2 plus 3i? No, it's just 2 minus 3i, because you just need to reflect along the real axis. That means you just change the sign of the imaginary part. Remember that? When you reflect, you change the sign of the imaginary part. And this should be multiplied by 1, but it stays the same. Okay, so I multiplied the numerator up here by 2 minus 3i. And I can't do that unless I also do it down here in the denominator. So down here, it says 2 plus 3i.
Times 2 minus 3.
So you see, I've multiplied the fraction by the denominator's complex conjugate. It sounds complicated when I say it, but what you actually do is not hard.
Let's try to continue calculating this and see what it looks like.
I can't do anything about the numerator, so I'll just copy paste it as it is. It shows 2 minus 3i. In the denominator, I can start calculating because it's a total sum. Multiply the difference of those two same numbers and see what you get, the square of the first number.
Minus the square of the second number.
That was one of the polynomial identities. Let's continue calculating this, and it gives 2 minus 3i. I've calculated it and can't do more with it, so I'll copy paste it. It shows 4, but here it shows 3i squared, meaning both 3 and I need to be squared, which gives 9i squared. But I squared is minus 1, and minus times minus gives plus. So it gives plus 9. So 4 plus 9. And now I hope you can see why this was clever, because look at what it shows now.
Now it shows 2 minus 3i.
Oh, what's pulling? And what does that give? Well, now I have to divide the fraction into 2 fractions. Because if there are multiple terms in a numerator, you must divide the fraction into as many terms. So 2 divided by 13 and minus 3i divided by 13. So a fraction where there are several terms in the numerator must be split into multiple fractions. Do not do this if it's just one numerator and several terms in the denominator. You must not split them into multiple. It creates a terrible problem if you try.
But here I may rewrite to 2/13.
Minus 3/13.
And then I'm done. Here is the result. Is this a complex number? Yes. How far should I go on the x-axis? It's 1/13. How far should I go down the y-axis? Because there's a minus. It's 3/13. What kind of complex number is this?
I don't know. I've completely forgotten what I did.
Oh yes, that is a complex number, which if I multiply by that one, should ideally give 1. If it doesn't, it's not a reciprocal number. And that can be tested. So let's just try to test if it's really true that this number has the property that if I multiply it by this number, it just gives a plain number.
It would be really nice if that's what we calculated, right?
And I hope at the same time that this helps you understand what it is I've done. I've found the reciprocal complex element for that number, and it satisfies the condition that if you multiply it by that number, you get 1. Otherwise, it wouldn't be the reciprocal. The reciprocal of 3 is 1/3, because 3 times 1/3 equals 1, as the words are defined. So let's just try to check it. Let me check if it fits. Is 2 plus 3i. If I multiply it by my result, which I just got, called 2/13.
Minus 3/13.
Then it should hopefully give 1. And now I can't stick to my own rule of never doing math in public, especially with fractions. But I'll try anyway. So let's try to work this out. That times that, what does it give? 2 times 2 is 4. So that gives 4/13.
Oh, just blow a tire.
That times that. What does it give? 3 times 3/13 must be 9/13. And then there's a minus. So it must be minus 9/13 I squared. But I squared is minus 1. So that gives plus 9/13. Count me in on that. What am I missing then? Then I need to say that times that and that times that. Here it gives minus 6/13 I. So I write minus 6/13 I. And when I multiply that by that, it gives actually plus 6/13 I plus 6/3. So we see that this one is as big, but with the opposite sign as that one, so they cancel out. So left issue, I have 4/3 plus 9/3. I have to add the numerators together. That's why it's called the numerator. I can count how much I have. So I have 13/3, but that might be 1 point something. So that results in nothing. So nicely it fits. This number has the property that if I multiply it by that number, I get 1. That's why this number is called the inverse or the reciprocal complex element.
Try!
It needs to be practiced. So here are a couple of tasks. And when I write them down, we pause the recording. So I've written down 2 complex numbers for you. One is called C1, 3 plus 4i. The other is called C2, minus 1 plus I.
You need to determine modulus C1
And modulus Z2.
Task 2. See that, you there. Multiply, then set your own complex conjugate.
And find Z2.
Multiply, so complex. And exercise 3. Definitely. The inverse element or reciprocal element to CU and the reciprocal element to CU. Let's pause here. Okay, let's solve those preliminary exercises on the board. In exercise 1, I need to find the modulus of Z1 and the modulus of Z2. Modulus means how far the complex number is from the origin. So we use Pythagoras. Then is the square root of A. The real part squared plus the imaginary part squared. And that's how you find the distance from the number to the origin. And we know that, well, here it's 9, here it's 16. So it must click the square 25, which is 5.
Now we're going to find the modulus of Z2.
And for that, we'll take the square root of the real part squared again. And we see here that the real part of Z2 is minus 1. So that's why I wrote minus 1 squared. And then I need the imaginary part squared. But there's a hidden one. So the imaginary part is 1. So here it's 1, here it's 1. And that should give the square root of 2. So there's the square root of 2 from Z2 to Orico. Now it's ready to stop in the queue. Now there's task 2. Here I need to determine Z1 times Z1 conjugate.
That means I should write plus phi I.
XZ3 minus 4A.
I could do it like that, but I could also use the fact that I know that Z1 times Z1 conjugate is modulus Z1 squared. So I can just take advantage of this right away. I found the modulus of Z1. It was 5. And 5 squared, well, that's 25, and that's the answer to the question. You could also say times this, times that, times that, times that, and add it all up. You also get 25. Exercise 2 will be Z2 times Z2 conjugated. Well, it's like the modulus of Z2. That means it's the square root of 2 squared, so it's 2. Now we come to the last task,
where I need to find the reciprocal element to Z1. But we've learned that I just need to multiply the numerator and the denominator by the complex conjugate of the denominator. So that gives Z1 conjugate over Z1 times Z1 conjugate. But Z1 conjugate is easy. You just take the number here and change the sign of the imaginary part. So it must be 3 minus 4i. And I've calculated this. It gave 25. I can just write it here. And then I can say it must be 3 over 25 minus 4 over 25i. 2 over 25. It's minus 24 over 25. So we're only missing the last question, which is to find the reciprocal of Z2. So 1 over Z2, and it's the same procedure again. It's Z2 conjugated over Z1. Second time conjugated. And Z2 conjugated, that must be negative 1, negative I. Because I have to write the sign for the imaginary part. So that's the only place I have to write the sign. And then I have to say Z2 times conjugated, but I didn't have that.
Calculate it. It gave 2.
So here it should say 2. And then I can split it in 2. So it gives minus 1/2. Minus this one here. Then it's done. All right, questions? Okay, we're ready for board number 7. Now we're going to look at something called argument. So the next subheading for complex numbers is called argument. Yeah, the next main heading, I don't think it should be argument.
All of a sudden, the first time for those of you who have been here.
I've written the heading argument. Sorry for that. I dare to say it's smarter and more pedagogical to take division first. So I'll just explain how to divide two complex numbers with each other. It's important. The easiest way to explain dividing two complex numbers is to just do it. So here's an example.
I'm just making up two complex numbers.
Here's a complex number, set 1. It's called 2 plus 3i. Here's another complex number, set 2. It's called minus 3 plus 4i. These are just some numbers I'm making up. It's not that important, but I just want to show you how to divide z1 by z2. So let's try to find z1 divided by z2. But before we do that, let's just recap what division means. What does 10 divided by 2 mean? It means the number that's multiplied by 2 gives 10. What does 10 divided by 5 mean? It means the number that's multiplied by 5. So what does z1 divided by z2 mean? It means finding the complex number, which when multiplied by z2 gives z. And then we can precisely check if it's correct that way. So to do this, I'll insert what I have, 2 plus 3a. And it needs to be divided by minus 3 plus 4i. Then there was an old trick. You cleverly extend the fraction by the complex conjugate of the denominator, just like we did before, when we had to find the reciprocal element. So we just do this. We extend by the complex conjugate of the denominator. So it becomes 2 plus 3i, as it was initially. And now I multiply by minus 3 minus 4i. Because this is indeed the complex conjugate related to minus 3 plus 4i. And I do the same in the denominator, writing what was there initially, minus 3 plus 4i. And then I multiply by minus 3 minus 4i. So in principle, this number cancels with that number. So I haven't done anything, just rewritten what I had into something new. But it says the same thing. And the reason this is super smart is because if you take a complex number
and multiply it by its own complex conjugate, you get a purely real number. What real number do you get? Modulus of the complex number squared. Do you remember? Z times Z conjugate gives modulus Z squared. And that's a real number because it's a distance from the origin to the number. So it's just a normal real number you get. Let's take a look. So what do I get in the numerator? Well, I get this times this. That gives minus 6. Then I do this times this. That gives 3 times minus 4. It's minus 12 squared. But squared is minus 1. And minus minus 12 is plus 12. So now I've done this times this, and I've done this times this. Then I do this times this. That gives minus 80. And then I do this times this. That gives minus 9i. And now the whole thing is calculated. I can definitely tell you about it. And it needs to be divided by the total sum. Multiplying the same two totals, they change. And it always gives the first number squared. Minus the second number squared. We know that from algebra. Let's try to click further on this. What does it say here? It says plus 6, because 12 minus 6 is plus 6. So it says 6. And then it says minus 8i, minus 9i. That must give minus 17i. And this has to be divided by. And here I get minus 3, the whole thing squared. Minus times minus makes plus, so minus 3. The whole thing squared gives 9. Let's note that minus 3 squared is not the same as minus 3. The whole thing squared. This gives minus 9. But this gives minus times minus, which is plus 9. If you've forgotten that kind of thing, I'm mostly hanging out with Jens and Harold. 4i squared must give 16i squared, but I squared is minus 1, and minus times minus, and plus gives plus 16. And what do we have then? 6 minus 17i, all over 25. And now we see why it was smart. But why was it smart? Yes. Why it was smart to extend the fraction with the conjugate of the denominator? It's smart because now the denominator becomes purely real. And now I can split the fraction into 2, and then I have the answer. So I'm saying the 6 should be divided by 25. And the 17i also needs to be divided by 25. And then, of course, we must remember to indicate that it's minus 17/25 I. And here's the answer. That's what I have. That's the number you get when you divide Z1 by Z2. What does it mean? It means that if you took this number right here and multiplied it by Z2, you should get Z1. If you just missed it, you could quickly discuss it as you'll get to practice multiplying again. So that's how you divide complex numbers. Here also see your warning. And this warning comes because I've spoken to my old colleague. My name is Jakob Martin Petersen, who's responsible for Mathematics 1 at D2. He told me that the students had been given an assignment called something with something like this. And then there were quite a few who said that 6 should be divided by 2. I can take that. And 6 it shall be, I'll give 2. And that's just nonsense. You shouldn't take a fraction and split it into 2 when there are 2 terms in a denominator and the numerator. An example that shows how wrong it can go.
If you look at the number, what should we say? 6 divided by 2 plus 3.
6/5. Aren't we agreeing that's what it says? 6/5. Don't we agree it's a number? 6/5 is a number less than 2 at least. Sounds good. Now try to split that into 2. 6 divided by 2 gives 3. 6 divided by 3 gives 2. 3 plus 2, that's 5, which is definitely greater than 2. It's completely wrong to split that up into that. So let's hurry up and erase so no one online sees an equal sign. I don't mean that equal sign. I don't mean at all. I only wrote it to show what foolishness you might do if you had a brain hiccup. So just watch out for that. But here I want to split it into two. Why do I want to split it in two? Well, obviously, because you can count the numerators. If you have one 3D label and then you have another two 3D labels, you can count how many 3D labels you have and say 1 plus 2. That's how many you have. So this is the same as 1 plus 2/3. So you're allowed to take a fraction with multiple terms in the numerator and split them into multiple fractions. But you're just not allowed to do it when there are multiple terms in the denominator, as that leads to nonsensical results.
Just a little warning.
So here are a few problems for you to try and solve. We'll pause the recording as soon as I've written it down. Problems now. Z1 is 5 minus 4i set to of minus 2 plus 3i. Problem 1. We got zeker overzetten. And task 2. CQ C2 over C. Now it's time for a break, Alexander.